Today we will talk something about navigation, and also we will get back to 10 years before, take a look at how people do DARPA Urban Challenge, how they did it. And next we will see it from Chris. And Chris is I think he's the CEO or CTO for the Google self-driving team. And the talk is in 2015. Interestingly, he actually not only just give the talk in TED, he also came to MIT when I was there, and I was in the talk in person. I think that's a great one. And we will definitely want to see what's the advancement from DARPA Urban Challenge to Google self-driving car. That's about like 10 years. Finally, we'll talk just a little bit about RAS navigation stack. Here comes a definition first, a definition of a robot. And this is from a textbook by Peter Cook. Okay, and the definition here is that a goal-oriented machine that can sense, plan, and act. So whenever you have a robot in a different form, you would imagine that the robot may have some sensors with some computation to plan and some actuators to interact with the world. The navigation itself guiding a robot towards a goal. Okay, and simply put, we want to see it in a human navigation way. We may think that we want to go from here to someone's office. Then you need to safely go from here to the stair, go up, and then you also need to know where to go, right? Here we got a more precise definition for navigation. And when people say something about navigation, there might be two very different aspects of how to get from A to B. The first one is called orientation. And it refers to the ability to know where you are and where you want to go. So this is orientation. And the second thing is about mobility. It refers to the ability to move safely, efficiently, and effectively from one place to another. And back to 2007, November, and the DARPA Urban Challenge. And I actually explained some of those in my earlier lecture, but we didn't really dig into how it works. So just some refreshment to remind you what's going on here. So there were 35 teams, and the first place was CMU, and then Stanford, and Virginia Tech, and then MIT. And some scientists in CMU and Stanford later, they went to the Google self-driving team. So that's what you can see 10 years later. This is the Stanford team, and actually the car looks not that different from what you can see for now, right? Still, there is a big Velodyne LiDAR on top. And you could also see all different sensors, maybe around or on top or somewhere on the vehicle. So again, a robot should have the ability to sense the environment first. Some computers should be able to plan, and then for a vehicle, just try to drive the vehicle. This is the vehicle from the MIT team. And I was inside this vehicle physically when I was there. By then, the vehicle was locked down in the basement of the SATA center, and we somehow tried to steal the combination of the lock and try to sneak into the vehicle, take some picture, and show off to people. Yeah. And actually, there are also lots of computation inside this vehicle. So if I remember correctly, they put a workstation, a cluster inside. So back to like 10 years ago, the computation is not that powerful yet. It's very interesting that the MIT team and the Stanford or other team, they took very different approaches for this problem. So the big debate was that the MIT team did not use a prior map. You may think that this is kind of stupid, right? Because the game is that you can use a map. But eventually, the MIT team, they did not use it. They used a fully perception-driven approach. That means it will do a SLAM. It will build a map on board instead of try to localize the vehicle inside a prior map. Let's take a look at the vehicle in action. So far, we have seen that it's kind of a controlled environment, okay, but it's still very exciting that like 10 years before, the car can do this thing by itself. How it works, here comes some system diagram over here, and you can see that definitely there are lots of sensors on top of the vehicle. Here comes the perception part. You could imagine that lots of LiDAR could give you the point cloud, right? And you want to definitely parse the point cloud some way to drivable or obstacles. And later on, you could see that it kind of built a map by itself. Our left-hand side, those guys, you could see a navigator, a motion planner, a vehicle controller over here. So those are more or less the planning part. Although the perception-driven vehicle did not use the prior map, still you need to give the vehicle a goal point so that the vehicle know which direction to go. You could see that here some steer, gas, or brake, and how to control the vehicle, and then come back to perception. It seems not that different from Ducky Tongue, right? Here is a planning part, and I would like to show you guys this video.
Here's an actual implementation from the Gazebo Urban Challenge, the Stanford car.
And actually, this vehicle is from the Stanford team.
The fact the car uses sensors to see obstacles, and obstacles are sometimes included, and the car can only see them when they're nearby. What's really remarkable here is that the car is able to plan really complex maneuvers to the goal. At any point in time, you can see its best guess group of the path to the goal, and the orange trees are A-star search trees. They aren't exactly grid trees. Our car moves differently from a grid-based robot. It can turn at different angles. And each of these little steps is a different turning angle combined with a different forward motion. But leaving this aside, you get these amazing trees that find paths all the way to the goal using A-star. This implementation is so fast that it can plan these paths in less than 10 milliseconds for any location in this maze. That was faster than any other driving team that I know of at the DARPA Grand Challenge or the DARPA Urban Challenge. The planning is repeated every time the robot cancels the previous plan. You can see additional adjustments at pace at times. But as you go through this video, you can see how A-star planning with a simple Euclidean distance heuristic is able to find a path to the goal. When you implement this yourself, the big difference to our grid implementation is a different motion model. You have to implement a robot that is able to turn, and you have to write on the math of a robot that's able to turn and go forward. This robot also can revert, so going backward is a discrete different action. But other than that, it's essentially the same A-star algorithm we just implemented. So if you want to build a self-driving car, you don't understand to make a really complex, nice search algorithm to find a path to go. So this is a scene where DARPA trapped our car using a barrier that went all across the street. So the only way for the car to navigate this was to take a multi-pole U-turn and then to plan this all by itself using A-star planning. The car pulls up to the barrier, realizes there's no path to go, then invokes its A-star planner and comes up with a turnaround maneuver that is not particularly elegant, but it's super effective. And the car was able, in this competition, by itself, to turn around using A-star, find the optimal plan to do so, and move on. Otherwise, it would have been stuck forever behind this obstacle. In this final video, I show you a parking situation where the car has to back into a parking space between two other cars. And you can see how the obstacles are visible, how these other cars are visible, and how our vehicle Junior navigates an actual parking lot. Again, this is using A-star. It finds its way optimally into this parking spot, backs in and backs out again all by itself. The planning time for each of these A-star runs is less than 10 milliseconds. And the car was able to competently do this, even though in advance it had no clue where the obstacles were and where the parking spot was. That is A-star for forward path planning. And what you've implemented yourself is the core of it. Again, if you want to turn it into a real robotic motion algorithm, you have to change the motion model. And you have to see the next class I'm teaching you when I go to continuous values and show how to turn this into a continuous.
So far, we have been talking about navigation without a map. So you could see that the vehicle tried to discover the maze with the A-star, right? And then it tried to localize and mapping, do the localization and mapping at the same time. Here comes a term about reactive navigation. Okay, so here comes some example. Heading toward a light. You could imagine that like a animal or insect can do this, right? Or following a line on the ground. Okay, moving through a maze by following a wall. Last one, vacuuming a room by following a random path. So here, actually, no map is required, not even building a map. You still have the sensing, but maybe minimum planning and react, to act, to follow, head toward a light, to follow a line or a wall, for example. I think this is a good talk. Actually, you guys can do something about it already. It's actually not that far from us. I will just introduce some of the package in navigation stack. From this figure, you could see that this one is more or less similar to the system diagram I showed you earlier in the class. We have like sensors, perception, some planning, right, and maybe some map. And then later on, it's more like a controller, and then try to give the vehicle command to a vehicle. You could actually see something similar. On our right-hand side, you could see a few sensor sources over here. And here is another ROS node called map server. So it actually reads more like a PNG image with maybe black and white, and tell you like this is the map, maybe 2D map. Where is the obstacle and what's the map look like? We also see something here like called move base and AMCL over here. So we have seen some of the similar component here, map server and move base. So we already have discussion about global and local planner. And maybe some of them, in some tasks, you don't really need a global planner. And AMCL, it's a probabilistic localization system for a robot moving in 2D. Also, you may ask, where are those maps coming from? So this is another famous package called G-mapping. And it used the LiDAR, the laser scan, and it could do SLAM. So do the localization and create the map at the same time.